Hello, everyone. Thank you for joining my presentation. I will now start the presentation of a journey towards the columnar data store. My name is Aya Iwata. I work for Fujitsu Limited, and I am involved in the development of Fujitsu Enterprise Postgres, a product based on OSS Postgres. I've been working with Postgres since 2016. The features I will present in this presentation will start discussions on the following thread. This thread also provides a prototype patch. We want to introduce these features and find people work with us on this feature. In recent years, analyzing business data and using the results to make decisions has been needed in every industry. Here are some examples. A EC business that sells products and services on the internet uses product sales data to optimize inventory. Financial service can help identify fraud by monitoring transaction history. In the manufacturing industry, data acquired from sensor is used to monitor machine performance, detect temperature rates, and predict machine maintenance timing. In the transportation industry, information such as location can be obtained periodically to optimize delivery routes and use road conditions to warn of delivery risks. A high search performance feature such as the columnar store is generally required to utilize business data for information analysis. This slide shows the typical features of the columnar store. The key feature of the columnar store is its fast research performance. In the case of the columnar store, you can scan only the data stored in the specific columns needed for data utilization. This reduces the cost of I/O and speed up searches. In this example, the columnar store database is on the right, and the ordinary low storage database is on the left. Suppose you want to look up product name and the purchase date from the purchase history table, as shown in the SQL statement in the example. In a plain low storage table, we need to scan all columns, including IDs and prices, which are unnecessary for this SQL. In contrast, a columnar store database can scan only the necessary columns. One of the characteristics of the columnar store is its efficient compression of stored data. Using the database for a long time increases the amount of data stored. In a columnar store, compression is performed on a per column. For example, dictionary compression has dictionary per column, each column. As in this picture, the same product name tend to appear in the columnar store. Columnar store compression is more efficient than row-wise data because it often contains the same words or numbers. Now, we explain what to do when you use the columnar store feature in Postgres. Postgres is a row-oriented database that stores data on a page row by row. Therefore, when performing data analysis using generated in business operations, columnar store or some in-memory feature may be used to improve scanning performance. Postgres provides several columnar store features as as extensions. For example, Citus provides columnar storage capabilities, which are also used in Azure Cosmos DB for Postgres. Also, Hydra extension and PG Mooncake extensions are available. These extensions have the characteristics of the columnar store feature, providing high scan performance and compression efficiency, but the bad performance for updates. The columnar store is not optimized for insert, update, and delete. This is because data is stored independently in each column, and all columns must be read and updated each time they are updated. This operation requires additional I/O and processing time compared to raw format storage. The figure shows an example of insert processing when an insert SQL statement occurs. In the column store on the right and the row store on the left. Suppose you want to insert new purchase history data with an ID of 555, product name Apple, price of 210 yen, and purchase date of May 1st. In the case of raw format strategy, you only need to insert the row once. However, a column store requires reading and updating of each storage column. On the first slide of this presentation, I introduced some example of using business data such as EC sites and manufacturing industries. These business data are constantly occurring. For example, on an EC site, purchase history and balance updates are constantly inserted. In the manufacturing industry, information for the sensor monitoring the machine is inserted one after another. In this way, data generated in the business is always inserted into the updates in tables. When analyzing data that has just occurred, it is necessary that the update performance does not fail while maintaining the performance of the columnar store. In other words, if the data generated in the business is used for analysis in real time, it is necessary to have the retrieval performance of the columnar store, including the latest data, while maintaining the update performance. Our proposal, Vertical Clustered Index, VCI, is designed to be useful in such case. Starting with this slide, I'd like to introduce our community proposal, Vertical Clustered Index, says VCI. VCI is a columnar store facility that uses columnar indexes. We are currently developing a prototype which is also being discussed in the community. The proposed patch is also in the thread. Here are a few things you can do with VCI. First, it is possible to aggregate business data generated by OLTP in real time. Second, you can speed up data retrieval. Describe the three scopes of VCI functionality currently in mind. The first is the columnar store. To utilize business data in real time, we have developed two things in VCI. A, to avoid degrading OLTP update performance, the data generated in converted to columnars asynchronously. B is to search all data, including newly updated data. The conversion to a column is asynchronously. In this case, depending on the timing, there may be update data that does not exist in the column. A VCI scan is designed to scan both data that is already columnar and data that has just been updated. And the current functional range of VCI's second one is data compression, and the third one is parallel scanning. I also plan to hold columnar store data in memory. This is a word picture of VCI. VCI introduces two storage structures to implement an updatable columnar store. One is write-optimized storage. The other is read-optimized storage. Write optimized storage is for reading columnar data. Write optimized storage is used for minimizing the impact of writing. Let me explore details with example, the next slide. From this slide, we will discuss how VCI works in the flow from creating a VCI index to updating the data as asynchronously and reflecting the column data. The following is an example of a product purchase history table. There is a table with purchase ID, product, a name of product, and price, and the date of purchase on column. This table adds rows each time an item is purchased. The first is when you do create index. When creating a VCI for a table, use the using VCI clause in create index syntax and specify the target columns for the VCI index, running create index to create a VCI. It creates read optimized storage, which says ROS. ROS is a storage mechanism that stores data in the form of columns. Just because ROS is created does not mean that it drops the original row format table. Run a query like create index, VC index, using VCI, price, date on the purchase history table, as shown in this example. This creates a ROS that stored only price and data columns data. Date columns data. So, okay, the index is now created. Let's see how it can be used for scanning the purchase history table. Data is already stored in ROS. Therefore, when a select statement is executed, the VCI looks for ROS data. This allows you to quickly search for only the columns you want, such as price columns or date of purchase. In this example, the select statement scans for price and purchase data, purchase dates stored in ROS. Okay, so we can see the VCI works for select statements, but what if the insert or update comes? When a new row is added to the purchase history table, the tuple ID, TID, of the new tuple is stored in write optimized store, says WOS. There are no changes to ROS in this time. Whenever an update is performed, such as adding, updating, or deleting rows from a table, WS stores the target tuple's TID and minimizes transaction information. The data inserted into WS is very small, so the transaction impact is low. This example inserts a tuple with TID 5 into the purchase history table. WOS then stores the tuple's TID 5. We do not insert price and date, purchase date into ROS. Suppose the select statement comes after insert. The price and the date column for the tuple with TID 5 is not on ROS. Therefore, the TID of WS is used to convert the data into local ROS, which is temporary ROS. Once the conversion to local ROS is done, VCI scan looks within local ROS and ROS. This enables searches to include new data that is only available in WOS. Converting to local ROS is somewhat costly, so the VCI plan should consider the cost of converting from WS to local ROS. Local ROS is temporary ROS, so that disappears after the execution of the select statement. With the update, the data that was in WS is not always in WS. After a while, it is converted to ROS by background workers who manage or control ROS. So the conversion from WS to ROS is performed asynchronously with the transaction. Once the conversion to ROS is complete, the TID is removed from WOS. So far, I've explained how to create a VCI insert into a table and select using VCI. I will share the results of the performance measurement. This is a comparison of TPCH scanning performance in my company environment. Measurements compare VCI parallel scan with OSS parallel scans. The result shows that VCI scans are about 4.4 times faster than OSS parallel scan. It is not an attached patch performance. This performance measurement, VCI has parallel scan, but attached patch removed the parallel scan part. The following example shows the DBT3 measurements. It measured on old version Postgres 9.5 base. Therefore, we compare OSS sequential scan with VCI single or parallel scans. For query 1, left side, 24 multiplex VCI scan are about 46 times better than OSS sequential scans, and query 19 was about 11 times faster than multiplicity of 24. The details result of these measurements in the table has been shared in an old VCI thread. Finally, the performance of the update process is measured. We compare the performance difference of update operation with VCI and without VCI. As a result, it was confirmed that there was almost no difference in performance, although the performance of VCI was slightly lower. In this way, even if VCI is set, OLTP performance can be almost unaffected. Now, let's talk about the current implementation of VCI. VCI is implemented using the index access method. Index access method is used to perform necessary operations on the ROS and WOS of the VCI at the time of insert, update, and delete. It also replaces the scan execution plan with the VCI plan by using the existing executor hook. And we use Postgres custom scan facility to implement 4 different scans that use VCI. And VCI has its own implementation of parallel scanning. This part is not included in the current patch, and parallel scan will be modified to Postgres standard implementation. And VCI also implements 2 new hooks. This implements hooks for index and relation operations. I will share the details of these hooks after this slide. The following are the items that may need to be implemented or changed or improved in VCI at this time. First, missing items. VCI does not support all data types. For example, text search related types and JSON types are not supported. And it is also does not use all table types. VCI is only used original simple table and unlogged table. For a wide range of users to be able to use VCI, we are looking to increase the available data types and the table types based on user requests and actual use cases. Second, VCI takes time to set up. Defining indexes on existing table data is time-consuming. For example, if you want to create an index for a table that has significant numbers of rows over many years of use, an early VCI setup can take some time. Finally, support for PG upgrade. The current implementation of VCI does not support PG upgrade. Therefore, a 3-steps process is required before updating a database containing a VCI. Step 1 is to verify and remember the VCI index definitions before migration. For example, using PG indexes. Step 2, remove the VCI extension before PG upgrade. Step 3 is to do PG upgrade, then recreate the extension of VCI and recreate the index on the table. Another feature that needed to improvement and discussion is the newly added hooks. As we discussed a bit on the previous slide, the VCI implementation added a few hooks. This is because some hooks were needed to convert between the ROS and WS of the VCI. The first hook we added is the delete execution hook. In the index access method, data deletion is triggered by vacuum. This leaves the deleted columns data on ROS even after it is deleted. In VCI, however, we want to delete data from ROS every time a delete statement is executed. Therefore, a new hook is created when a new delete statement is executed. The second hook we added is described below. With the introduction of the hot update mechanism, an update on a column that does not have an index will not call AM insert. If AM insert is not called, the VCI cannot write the TID of the updated rows to a WOS. For example, if the insert is followed by the update on a non-indexed column, and then the update tuple is deleted, the deleter will specify a TID that does not exist in WOS. To prevent this from happening, we have added the hooks that are called on updates of columns that do not have indexes. As you can see, there are many items to be discussed and improved. So we welcome your participation in this vertical clustered index discussion, and let's develop vertical clustered index together. Thank you.